I can't thank Stan enough for giving me this great introduction, and Ben too, to really talk to you today about what we do in advanced computing at the University of Texas. And the great thing is that while we are normally science-focused folks, we have a lot of stuff that we do that will be usable, I think, for the market research that y'all do. I'm going to talk to you today about some of our technology, some of our big information problems that we're doing, and then hopefully we'll relate to something that you're working on, and then we'll go from there. So without further ado, I came across this quote in The Economist the other day. It says, "It's a very sad thing that nowadays there's so little useless information." Anybody recognize that? It was said by Oscar Wilde in 1894. Okay? And so even at the turn of the last century, there was already this overflow of information. And now today, with digital records, digital communication, not to mention all the social media we have, it's true now more than ever, the age of big data is here. But what do we really mean by big data? Of course, we're talking about text, documents, PDFs, surveys and reports that you might generate, but also email, status updates, tweets like we saw from Bluefin. But we're also talking about numbers, metrics, quantities. Your budgets are also data. Also locations generated by RFID tags, GPS, and also images and videos. But even beyond that, we're also talking about the analysts that you create from the initial data. So all of those intermediate reports and the final reports that you submit to your superiors or to the public, that's data also. And then the metadata describing the original data, is this a PDF? These tweets are from this time frame. That's data too. And so we enter into this recycling and ever spiraling upward mountain of data. So let's talk about the age of big data in terms of records. 15 sectors in the US have more information today than the Library of Congress, and that's about 235 terabytes per company. And as of 2010, 5 billion mobile phones worldwide, RFID tags are expected to jump to over 200 billion by 2021, and smart meter growth is projected to grow from 130 million to 340 million by the middle of this decade. Oops, wrong button, sorry. So let's talk about other forms of big data and communication. As we heard from Pradeep on day one, Facebook in 2011 averages 30 billion pieces of content shared every month and 770 million page views every month. Those numbers have only increased to today. And on Twitter, the time for Twitter to reach the first billion tweets was 3 years. The time to reach the next 1 billion tweets, 7 days. Yeah, think about that for a second. That's Texas size. We're talking about average tweets per day. March of 2010, it was 50 million. February of 2011, 144 million. March of 2011, 177 million. 30 million increase in just 1 month. And it's just getting increased. And then on Reddit, we're talking about a first billion page views from its inception to February of last year. And then it took to get to the next billion page views later that year. Only 10 months. And we're not even talking about Tumblr, Pinterest, Foursquare, and the latest social media outlets today. So are we going off the cliff here? What can we do to help address just accumulating all this information, and then how to provide insight from the analysis of it? So one solution is you can pay for it. You can get McKinsey, Accenture, IBM, American Express to analyze this data for you and provide you a nice package. You can try to do it yourself. You can invest in infrastructure. You could hire Google or Amazon to host software for you to do this, or you could develop your own software or purchase a third-party program. But if you're hosting it offsite, there might be some security concerns about what you want for folks to have access to this data. And so a third option, and one that I propose, is to partner up. So there are universities, research labs, and computing centers like TACC, where I work, that have the access to the hardware and have the expertise to help develop these projects for you. And so that can be a third road to get you started, and either as a justification to buy infrastructure yourself, or as an ongoing partnership moving forward. So TAC is part of the EXCEED, the Extreme Science and Engineering Discovery Environment. It was, that's the new version of the TeraGrid, if any of you have heard of that. And so there are universities and research centers across the nation that can partner and provide you these services. TAC is just one of them. Of course, it's the one I like. And there are also Department of Energy labs across the nation too. Those tend to have to be more mission aligned with your data, maybe not as much of an option, but I just wanted to let you know about them. And so let me tell you a little bit about TAC, where I work. Attached to the University of Texas, we're in the Vice President's of Research office, so we're not attached to any particular college. And we provide national cyber infrastructure. We get grants from the NSF. We just recently won a $50 million grant to provide the next big supercomputing resource to the national cyber infrastructure, to scientists all over the country and really all over the world. We have over 100 full-time staff and students, and we provide not only high-performance computing, but data and visualization services and remote services that folks can take advantage of wherever they may be. We also have an industrial affiliates program that allows companies to get access to those systems. And if you're interested in learning more about that, please talk to me afterwards. So let's talk about the systems that we have. Of course, high-performance computing is the bread and butter. We have two of the three largest academically hosted supercomputers in the nation. Ranger started off as number 4 on the top 500 list, a ranking of the power of supercomputers, and it's still number 25 today, which after nearly 4 years after its deployment is pretty remarkable. And as I mentioned, we just received a $50 million NSF grant to create Stampede, which will feature not only the latest Intel Xeon chips, but also their new Mike architecture. It'll be the first large deployment of that. Data mining, we have 1.2 petabytes of spinning disk attached to Corral, and then we have a tape archival system, which is 40 petabytes. And yes, everything has to have a Texas name for the systems. Visualization and analysis. Longhorn is the largest system dedicated for visualization and data analysis in the open science community. It has 2,000 cores and 512 GPUs. You know, there were some gamers and game companies in the audience. It's a very powerful rendering system too. We also have Stallion, which is the world's largest high-resolution tile display at 307 megapixels, and Lasso, which is one of the largest interactive and touch systems in the world at 12 megapixels. I'll tell you a little bit more about how we create those systems and how you could create them too. Basically, we use commodity hardware, and we leverage the growth in games, not only in GPUs, but in the displays for gaming industry and for entertainment to create large-scale systems. So a 3x3 display of 30-inch LCD monitors can fit in an office, on an office wall. A 5x3 display can fit in a conference room, and if you go 15 by 5, like our largest display, you need a dedicated lab for that, but it really provides you an amazing amount of resolution for the space. If any of you have seen a Cowboys game at Texas Stadium, either in person or on TV, you know they have a 60-yard Jumbotron that scans the entire field. Now that's physically larger than our display. It's only about 34 feet by 10 feet, but it has lower resolution. It's still 1080p, which you would get on your television, and each pixel is about that big. And on our display, even though it's physically smaller, you can show much higher resolution, much more data for you to analyze and gain insight from. So, one word, I'll show you a movie in a moment about the tile display, and you'll notice that it has bezels on it. And I suggest that don't worry about that, because for our users, the first time they come in the lab is when they most notice them, and by the second time and the third time, they look through them just like you would look through a window. And if a piece of data that you're interested in is beneath one of the bezels, if you were looking out a window, you move your head, you just move the data, and it works fine. The only thing it doesn't work great for is text, because if that if that word or fragment of the word is underneath that bezel, you really can't see it very well. And so we have projection systems that help for the presentations, and then the large-scale data on the big displays. The other thing is there are companies that will modify commercial displays and remove the bezels. Problem is they cost more and they're harder to replace. And so if one of these tiles goes out, we can just take it off, put a hot spare in, and we're good to go. You can get thinner bezel TVs, but you lose resolution. I won't go into it, but there's a ratio between how thick the bezels are and what resolution the display can be. And so you can use 46-inch flat panel, 55-inch flat panel that have very thin bezels, but it's still going to be just 1080p resolution. And you'll see an example of that with our touch display, which is using 46-inch TVs that have very thin bezels. Okay, so let's take a look at the high-resolution displays we deployed. So we started off with a 3x3, again, all 30-inch monitors, and then we went to the 307 Monster, 75 monitors, and then the College of Education contacted us, asked us to build them one in their own building, 3x5, kind of a nice in-between. And the great thing is that the smallest display can be had for maybe about 30 grand list price. The intermediate one, maybe about 120 to 150. And the top one, of course, is more, but very affordable compared to 10 years ago, a projection system with 2160 by 768 resolution. In other words, half one of those tiles cost over $1 million. So that's where the power of commodity has really brought us to a high resolution for an affordable price. And we're a university, affordable is good for us. Okay, so I'm going to play this movie. And this shows the software that we've developed for controlling the display. And this is open source software, freely available to anybody. And so you can see we have many very high resolution images. These are from the Google Art Project. And then we also are doing development with the Kinect gaming system to allow for touchless control of images on the display. Thank you, someone got it. And we're also allowing control for mobile devices using TUIO interface. We think that looks like Robert Downey Jr. And it's, of course, proven across Linux and Mac OS. There's no need, there's nothing really keeping us from building this on Windows. We just haven't had a need to do it yet. And so you can get a sense of the full size of the display there. Okay, so why do we need to go big? Well, let me give you a little example. So that is to scale the size of a 30-inch monitor. You can see where I might be going with this. And so that is to scale 75 of those put together. And then this is to scale a 3.5 gigapixel image from NASA, showing the entire Earth at half-kilometer resolution. And so you might not be interested in geography, but imagine if that was a network showing all of the interconnections on Facebook. You would need something very high resolution to show that in its entirety, or a large portion of it, certainly more than you could get on a single screen. If you've ever used something like Google Maps, Yahoo Maps, you have to pan and zoom, right? You scale out to see the large picture, zoom in to see the details, but you lose all of the related information around it. On a larger display, you can get both. So you can see both the detail and the context, which is important. There's research out of Virginia Tech showing that having that physical navigation of a display, just like if you were looking at a painting in an art gallery, really gives us better insight because we're more used to moving up to look at something close or stepping back to get the big picture. Okay, so this is an example of Botticelli's Birth of Venus on the big display. And the nice thing about this is you don't have to go to Florence to see this. And you get a very different interaction with it than seeing it in the gallery. You can actually zoom in on a single brush stroke and fill the screen. Pretty remarkable. But a screen this size also allows us to see correlated images. And again, see them all at once rather than flipping back and forth on a single screen. So for instance, this is artist Ben Rubin. He recently did a piece dedicating the Walter Cronkite Plaza at UT, and so these are some of his other works. You can see in the bottom right corner from the New York Times building, a piece he did. This is something we created to send the Aggies out of the Big 12, just showing Longhorns' football victories over the Aggies. So we can do both ways, but let's also look at the touch screen, and this will show the actual construction and use of the touch screen, and this was just done by one of our staff members and a student over the course of a few days to put this together. So this is really something that's accessible to folks like you. And so this is something that we've used for data analysis of the National Archives, and I'll tell you a little bit more about that in a moment. So you can see that some of the design sketches. Was an engineering student, so he was able to really get deep into this. But this is something just made out of commodity parts, a single node and 6 screens. We're using an AMD card that has 6 video outs. And so this can run Linux, Windows, anything that's multi-touch enabled, it will work. And the interesting thing is that what we did is put an infrared frame around the screen, and so that can measure 32 independent touch points. And the challenge is getting the software that will actually use that many touch points simultaneously. But things like Google Earth works fine. Bing Maps from Microsoft, before it got canceled, works fine too. And so here's the time-lapse construction of the frame. And so basically they did this in 3 evenings. Could have done in a single day if they had just done only that for that time. They're very proud that they were there that late at night. All of that framing is from a company called 8020. And what we did is we just made a design in Google SketchUp. Any device that gives accurate measurements, sent them to design, and they UPS'd us something a week later that had all those parts, and we were able to assemble them ourselves. We did the same thing for the large tile displays too. I love that part, seeing all the screensavers in it at once. So now they're installing one of the key things too is we put a big sheet of glass across it so you get a smooth touch experience across the bezels of the monitors. You don't have that hump that you might in other displays. So this is a little demo that came with some of the driver software showing a jet engine. And this is Bing Maps. You can really get into the city where both Bing and Google have really nice renderings of the buildings. And I'll show you an example of what we're doing with Google Earth to show geospatial data. Okay. So, nice tech, but what can it really do to help answer research questions? I'll give you 2 examples of large data projects that we're working on now. One is the Pecan Street Smart Grid Initiative in Austin, and another is the partnership with the National Archives. Both have the massive data challenges, and hopefully you'll see something similar to projects you're working on that we might be able to address too. So let's talk about Pecan Street. Has measurements of about 200 homes in Austin that have signed up for this research project where they take actual circuit measurements every 15 seconds. So washer and dryer, refrigerator, And to help address this, we started off in a traditional SQL database. We've transitioned to column store formats, InfinityDB and Greenplum, that was just bought by EMC. And those have allowed us to get interactive reads from this massive data and still be able to store it effectively. And so for project expansion, this will soon grow 200 homes now. They want to grow to over 1,000 homes across Austin and into the Dallas service area. Finer grained readings, we're reading at 15-second intervals right now. We expect that to move down to 5, and there are some circuit measurement tools that can go down to 1-second readings. And more circuits. So the Miller neighborhood in Austin is the densest collection of photovoltaics, of solar panels in the nation, of residential storage. It has over 1 megawatt of generative capacity. And I'll tell you why that's important in a moment. It will also be the densest residential electric vehicle neighborhood in the nation. They have 100 Nissan Leafs and the Chevy Volts that will be in the neighborhood. And then they also look to get to battery storage for homes, really just revolutionizing how we consume energy and how we can generate energy and return it back to the grid. So this is a view of a data portal that we created because we don't want to ship nearly a terabyte of data across to all the folks who actually want to make measurements of it. So we created a web portal that shows some statistics of the data and has the growth trends, and then also has the ability to do basic analytics right there in the web page. Graphing, this shows air conditioning consumption against whole home consumption for a day in August. And that turned out to be really important. This is something that kind of makes sense, but has never been quantified in this way before. The red is whole home energy usage, and the blue is air conditioning for an average over August of last year. And that August was the hottest month on record anywhere. We had over 40 days of that summer directly over 100 degrees. Very hot. And the air conditioning is a major component of consumption on that. And another way to look at it is we put this into Google Earth and showed the neighborhoods. These are anonymized by census block, just so you don't know exactly which houses these are. And so that shows energy usage at 7 a.m. on August 15th, and that shows it at 7 p.m. So we can see that average chart, but this dramatically shows not only the level of consumption, but where specifically the consumption is occurring. And so we can use this as the database grows to direct perhaps incentives to home users. If their air conditioning is really inefficient, we could direct rebates for new air conditioning. If their house heats up a lot right after the air conditioning turns off, we could target rebates for insulation or for better windows to help contain the cooling once it's been generated. So this allows us to really ask some interesting questions based on how people are consuming electricity. So this is the August average, again, consumption. And then having this density of solar panels allows us to see how that matches with the consumption curve. You can see that it's off a little bit, but generally there's a pretty good match. But then we break it out by homes that have south-facing solar panels in red and west-facing in purple. And now we see that west-facing actually matches that curve much better than south-facing. And that's because the south-facing peak, if you see, that happens at about maybe 1 or 2 in the afternoon. Folks are still at work. The west-facing PV, however, peaks at about 4 p.m. People are starting to get home, realize it's hot in the house, crank up their air conditioning. And why is this important? This is the spot price of energy. And so you can see there's this massive peak right at about 4 o'clock in the afternoon. Specifically, $850 for a megawatt hour of electricity. And the problem is the utility's break-even point is typically about $60. So as long as energy is below $60 a megawatt hour, they're making money. When it goes way above, they're losing money. And so not only are there brownouts and possible blackouts that we have in Texas when everybody cranks on their air conditioner, there's also utility losses that don't go accounted for. And so what we see instead, so here's general consumption, the top level. Solar, south-facing solar, does a pretty good job. It cuts total demand by half. But with west-facing solar, we actually cut it by over 2/3. And so what this tells us is that utilities should provide incentives for solar, for people to put solar panels on their house. But they should specifically incentivize west-facing solar, because that will help address the peak demand that folks see, particularly in the south during the summer. Okay, so let's talk a little bit about the National Archives. They have asked us to help address their massive data problem produced by presidential administrations. Presidential administrations, the Bush administration produced 300 million digital documents. It's expected that the Obama administration will produce over 1 billion. And these aren't just single records in the database, these are pages and pages of documents, PDFs, potentially hundreds of pages for the laws that have been passed. And they want some sort of visual inspection and analysis methods, because it doesn't make sense to look at 1 billion documents in the file, in your file folder readout. And so we're employing also novel word vector, paragraph-based searches for related document content. And so this allows us to pair documents together that don't necessarily share the same keywords, but share similar directions in vector space. And so it allows us to match for things better than say, a Google search would. However, with this project, we're still dealing more with what we have than with what we know. The sheer volume of digital documents is still the challenge to just organize those, and then we'll move on to making sense of all the documents. So we're creating a panel for them so that they can actually access and understand the documents that they have. This looks a bit like a Mondrian painting, but it has a key to the type of content and to the locations of that content. So for instance, if the National Park Service wanted to understand how many images they're serving on their web pages, this could give them a very simple answer rather than having to search through all their files. So this is using Java, JavaScript, R, also Python. There are a lot of powerful analysis tools out there just in the open community, and I definitely encourage you to take advantage of them. They are what we use, and so it can be very powerful things. We also have hierarchical file layouts that are correlated with file size, so you can understand exactly how deep your directory structure goes. Then we also can visualize numerical metadata, understanding the types of files that are within these each directory. And so combining the hierarchical layout with the numerical metadata helps us understand exactly what we have. And then they can pull out just basic analytics off of that screen. So multiple different views, and this goes back to why we have those large high-resolution displays. So we can see these multiple views at the same time rather than having to flip back and forth. So let me close. I hope you can take away a few things from this talk. That commodity hardware is your friend. It can really help you produce large, powerful tools and systems for relatively low costs. Open source software can take you a long way, maybe not all the way. For the Pecan Street data, we're having to go to proprietary solutions just to handle the queries. And that if you want to bring the analysts to the data, not ship the data around to the analysts. So portals and web-based interaction is increasingly important. And then finally, I encourage you to partner up with the communities that deal with this regularly to give you access to the hardware that's already out there so that you don't have to build your own. And with that, I'll open up to questions.
All right, thank you, Paul. Do you have any questions from the audience? All right, I have a question.
Sure.
In terms of data visualization, it's, you know, I think as researchers, we get the big analytics, we get the big data part, or we're getting there.
Yep.
But the visualization part.
Yep.
So it's a really hard task to accomplish successfully because you have the mix of, you know, left brain analytics and, you know, hard data crunching mixed with some form of artistic visualization in a way that people can, it tells the story.
Yep.
Like Stan was saying, it has some sort of insight-driven approach to it that the C-suite can understand and that we can make decisions based upon.
Yep.
How are you guys tackling that attack, and how are you looking for, you know, whether it's the right students, whether it's the right, that skill set, what are you looking for so we as researchers can tackle those same things?
It's really all of the above. And what we find is it's an iterative process because you not only want the information to be displayed, you want it to be compelling. People to come and say, hey, what's going on here? I want to understand this visualization better. And what we typically do is iterate with the subject matter experts to arrive at a particular solution. For instance, there are disciplines that have particular color conventions. Astrophysics really like red and blue, the rainbow color scheme. May not be the most effective in terms of understanding the data visually, but it's most effective for them to communicate with their colleagues. And so that's an example of working in conjunction with folks. Now, data in terms of analytics is harder because there's not necessarily a direct 3D analog. I can't just say, if I'm doing a visualization of a hurricane, I kind of know what that looks like. A bunch of clouds, maybe some speed and pressure of the wind, but if I want to visualize my Twitter followers, what does that necessarily look like?
And so, how is it engaging as well? How do you get the users to engage with that data?
Exactly. And so, basically, we'll look for a few things. One is understandability. You know, how is, if I put my Twitter followers out as little bird icons, does that may convey the number, but that may not be necessarily the best representation of what I'm trying to get out of it. Maybe I'm trying to look for geographic locations. And so maybe the Google pin map might be more effective. But then I also want to put it in a way that is compelling. And so, unfortunately, it's like knowing a racehorse, that you know one when you see one. And so it really takes that iterative process and working with your partners to arrive at that best solution. I wish I had just a button.
No, I think it's something that I mean, are there other people in the room that are struggling with that same thing when it comes to looking at data and analysis? But there's some great souls that say the couple each other. So it's something I think that we as an industry really need to look at and tackle. So I think it's an interesting thing.
Yeah, absolutely. And there are great tools out there like D3, Prefuse, that have some of these algorithms in there that you can easily attach your data to get to that first step. And really, often we just need that one thing to talk to that we can then develop.
Absolutely. Any other questions for Paul?
Yeah. I've got a question here. With all these high definition displays that you showed, which I can see how the analysts would get into the data and you have the definition to do the analysis there, does that mean that the analysis will be restricted to, I don't know, universities or places that have these high definition displays? And how does that how does that translate to, I don't know, clients that want to do analysis or other analytic houses?
So the question was, the displays are great, but do we have to bring the analysts to those displays, or are there other solutions? It's a great question. So one, it always helps if the display is local. You know, there's the getting people out of their office to come down to the lab challenge, and we try to answer that by making them easy to use and having these compelling visuals that you can't get in your own space. However, we are exploring the use of digital cameras with remote control and high definition cameras so that you can get some idea. If you're not local, you can still have that same exploration experience on the display just with sufficient resolution to come through digitally. And then third is we are developing methods that make these very affordable. And so even the small display could be had in a research budget so that you can connect, and then those displays can connect and have multiple displays and shared display across geographical distance. Good question. So the question was, in San Francisco there was real-time Instagrams, and that's definitely something we could do. What that would pair is the processing power plus the display, I assume, of the imagery. And so that's in the line of this capability. Because what's driving the large display isn't just a single machine, it's a cluster that has its own computing power. And so we can do simulations on that cluster or remotely to the big machines at our main lab and then display the content interactively. So yeah, that's what we're aiming for.
All right, let's thank Paul one more time.
Thank you.